known results held concerning degenerate equations also belong to this class of problems. In classical formulation in scalar valued cases, problem was considered by mathematicians Lerner, Repen, and myself. You see, and they establish the correct solvability of this problem in scalar valued case in classical statements. Subsequently, this problem was studied with regard in various functional spaces such as grand spaces, Lebesgue spaces, their weighted versions, and which we listed in reference part. Here, we consider more general case. You see, in Bochner, Orlich versus Orlich, Sobolev versions of this problem. Next part is notations. More general, they are standard notations. I push it, and then we, for solving this problem, we offer test spectral methods. For this reason, we firstly define the related topics such as T-basis properties, and here we define the corresponding concepts. So let X, Y be Banach spaces, and we denote by X, Y their tensor product algebra, tensor product, and let X tilde Y is some Banach tensor product of these spaces. Corresponding norm we denote by the following way. For simplicity is the following, we elementary tensor product of corresponding elements we denote by a simple X, Y. And here we denote, firstly define T-span generate of the subset M of Y by the following relations, analogously to the case coefficients we take from the space X. And then we define the concepts such as T-completeness, minimality, and T-basicity by the following definitions. First definition, one is the T-completeness. This means that if Y some system from space Y, then by LTY closure, if coincide this coincide with the considered Banach tensor product of spaces X, Y, then we say that this system is T-complete in this space. And in this case, the classical concept of orthogonality takes the following form. Let TK is the family of bounded operators which acts from the tensor product of these spaces to X. If regarding this the system Yn, these operators satisfy the following relation. We say that these operators, the families of these operators is orthogonal to this system. And in the definition 3 is defines the basicity of the considered system Y. In this tensor product, it is the direct analogous of the classical case. And in this case also is valid the following criterion for basicity. Namely, the system Y forms a basis in the considered Banach tensor product if and only if the following conditions hold. This system is dense, and this system admits a biorthogonal system, and the corresponding projectors are uniformly bounded. Then, in the following part, we give the necessary information from the Orlich space theory. M is let some Young function, and here we give standard constraintic for constraintic Orlich space, and perhaps I push it. You see it here, and also we need the concept of Boyd indexes of Orlich spaces by using the following function hash tail, as we define by the following relation, where m minus 1 is the inverse of the function m. And the Boyd indexes lower index alpha m and the upper index beta m are defined by the following relations. Here we give some properties of these indexes, and we essentially RM on reflexivity of Orlich space, and concerning continuous embandings regarding the Lebesgue spaces. And as I said, Young function Orlich spaces Boyd index which belong to the interval 0, 1, we denote by n01. And here we define Orlich Banach space generated by normorph Orlich space by the following relations. Also, perhaps I push it. You see it here, and using this norm of this space, we define Orlich space on rectangle P by the following norm. And firstly, we prove that this space is a base space or Banach space, and based on this norm, we define the corresponding Bochner-Orlich Sobolev spaces by the following norms. And in the following, we also need some facts concerning tensor product of scalar valued Orlich space and considered Banach space X. We established that this LM considered Bochner Orlich space coincide with the tensor product of these spaces, where the norm we define, we take norm of Bochner Orlich space. And we also need the concept of so-called UMD property and conditional martingale difference property, very known concepts. Here you see corresponding definition. And also we use the following very meaningful result of very known good mathematicians Rubio de Francia. The theorem asserts that the considered let Fs is the Banach function space or measure space S with measure mu and the XP base space, and the Fsx is the corresponding Bochner Banach space. Then this space is Umede space if and only if both the considered Banach space effect and the X are Umede spaces. And here we give also some concepts such as Radon-Nicodim property, Fourier type, and also perhaps I push it. Then we consider x-value trigonometric polynomials which has the following form with coefficients from the considered Banach space X. And the set of such polynomials we denote by px. And it is very known that if X base space, then Px is dense in Bochner space when P change from 1 to infinity. Then we have established the following theorem, which states that if X has OMD property, then the system of exponents forms the basis for Bochner space for such P, and moreover the following sums Rm projectors are uniformly bonded. This is a direct analogous of the very known risk property of system of exponents. And so if the Young function, the Boyd index of Young function M belongs to the interval 0, 1, then the system, exponent system forms, it is very known result. We use it. Here we give, also we use the concept of same regular boundary, uniformly same regular boundary domains, and here we also give the one results from the following work, where it is established that if the considered domain has uniform Lipschitz boundary, then there exists trace operator which boundedly acts from the considered Sobolev Banach space WP1 to Bochner space, corresponding Bochner space on the boundary. Using this result, we firstly establish trace space and the trace operators for our case, and the resulting the result concerning these operators, it is well as the following proposition, where G by GK we denote by the corresponding parts of the rectangle EK. Here we establish the existence of the trace operators, and also we essentially use the following lemma, where by G E we denote the corresponding trace operators in scalar valued sense, and establish that for every functional from dual space, we have the following relation. And in the following part, we also give some analogous of classical one of properties of four differentiable x-valued functions. Here we establish concerning needed properties. For example, corollary 27 means that if X have radon-Nikodym property, then the following relation holds. Where by GE we denote the corresponding trace operator corresponding to the boundary path E, where E denote the interval 0 to P on real axis. And after that, we establish trace operators. We can give consider the following boundary value problem: 3132, where also by GE or G0 we denote the corresponding trace operators corresponding to the boundary paths E and the boundary paths of rectangle P. And for solving this problem, we have a tensor spectral methods, which is direct generalization of corresponding scalar valued case. Namely, we consider the following spectral non-local problem, spectral 3-3, and the eigenfunctions of this problem are cosinus and ecos, and this each agent for each eigenfunctions has one associated function, which is we denote it by YMS equal to x prime sinus and ecos. And consider the following systems. These systems are orthogonal in LP. We established that this are orthogonal also in Orlich sense. And here we establish the basicity of these systems in considered Orlich-Banach space LM when X has omega property and the Boyd indexes of Young function M belong to the interval non-zero. Here we establish corresponding result, and after we also need the risk property of these systems. Firstly, we give corresponding definition. This is definition 31, and then we establish that by also above conditions on considered Young function M and the ecos. This system has Therese property in considered Orlich-Banach space. Also, we using these results, we establish this property of root functions of considered non-local spectral problem. This is theorem 33. And we using of these results, we firstly establish a uniqueness of considered boundary value problem. This is if young function M belong to the class N01 and the X belongs to AMD class, and the F belongs to the Orlich corresponding Orlich Banach space, then the boundary one the value problem 31, 32 has a solution. If this problem has a solution, then it is unique. Regarding existence, we establish the following theorem. Let M be young function if has Boyd index which belong to the interval 0 omega space, and Fourier type Q equals 1 divided beta m, where beta m is the upper Boyd index of young function m, and therefore boundary function f belong to the Orlich-Sobolev space, which at points of the interval 0 to p satisfy the following conditions. Then the considered problem 31, 32 has a solution, strong solution, if and only if the following condition integral form 3, 4 satisfies. Moreover, for solution, it holds the following estimate. It is our main result, and here you see reference, but I will demonstrate it. Here we give corresponding literature, and I finished. Thank you for attention.
All right. Thank you so much for the interesting talk. Are there any questions for the speaker? All right. If there are no questions, I would like to ask a question. Maybe this is a naive one, but this UMD condition, what happens if you don't have that X as this unconditional martingale difference condition?
Can you repeat your question, please?
Of course. I was asking about the UMD condition on X. I mean, you mentioned that you need it for some convergence of the Fourier series, but what happens when you don't have this condition, this UMD condition on X?
UMD condition olması gibi
Evvel mən bunu nötər tərcümə edeyim ki, bu olmasa yəqin ki, nəticələr doğru olmayacaq. If X hasn't OMD property, then I think that firstly, these methods don't işləmir. Don't applicable, and in general, I think that the corresponding results in this case will be not true. I think for these results, OMD property is necessary, I think, but yet we have not proved it.
Okay, sure. Thank you. Let's thank the speaker one more time.
Thank Thank you again. I wish you success in your work. Mm.
All right. Just a minute until the next talk, so we can settle down. All right. The next speaker for this session is Dikranyan, who is going to talk about making the group of 01 sequences connected. Thank you.
Thank you. Thank you. I forgot to put my name. It's just not out of modesty. I just forgot. Pardon? Are you the correct speaker? Yes, I am the speaker. So first of all, let me thank the organizers and in particular Pira Barbieri, who is one of my favorite co-authors. We wrote so many papers. Yeah. It's amazing, such a nice place. And I thank all people present here because they sacrificed a wonderful morning to come to hear my talk. Is it okay? Good. Okay, let's go. So I dedicate this to the 65th birthday of my co-author. So in 1944, Paul Halmosh succeeded to put a compact group topology on the group of the reals because the reals are not compact, as we know. And so I will call virtually compact an abstract group that admits a compact group topology, so that Halmosh proved that the reals are virtually compact. And he asked a description of all virtually compact groups. And this question was very fruitful because Kaplansky first gave a partial solution, and then also Harrison and Hulanitsky finally resolved this problem after 50 years. But in doing this, a lot of new concepts were introduced, especially by Kaplansky. So this problem was very useful. I will consider in this talk virtually connected groups. I mean, groups that admit a connected group topology. So my talk is dedicated to these virtually connected groups. So if you take the group S of all 0-1 sequences, under the coordinate-wise operation, this is a group, of course, and if you put there the usual product topology, it is compact, but it is not connected. It's even totally disconnected, as far as possible from connected. So one may ask, is this group virtually connected? Can you manage to find a connected group topology on this group of sequences? Well, Markov succeeded to find in 44 such a connected group topology on the group of sequences 0-1. And he asked this general question: describe all virtually connected groups. So my talk is dedicated to give a partial answer to this, which is a complete answer in the abelian case. So first I will give some early solution, early birds, and then a necessary condition for being virtually connected. And then what is important and what makes this talk eligible for this conference on analysis practically is a main tool I am using is a space of functions, because analysis is nothing else but the study of spaces of functions. So this is a very useful construction, and there will come the proof of the main theorem. If I have time, I will also see the details of these proofs and discuss the non-abelian case to see why there is no solution. I mean, Markov's conjecture fails in the non-abelian case. Okay. So the early birds. So from now on until the last slides, all groups will be abelian. So in 46 and 48, Markov and Graf constructed connected group topologies on every abelian group of size kappa bigger than or equal to the continuum and of exponent 2. It means all non-zero elements have order 2. So how they did it? They considered the free abelian group generated by a compact Tikhonov space X. So this is simply the free abelian group with a spatial topology on it. It's too complicated to explain it and not necessary for the talk. So I will not do that. And in this group, the subgroup 2 times F is closed so that the quotient is exactly the needed connected group of exponent 2. Other construction also appeared. Meanwhile, 2 parallel and almost equal, very similar construction, one by Mutilin in 66, and in the same year by Waterman and Bergman. They actually constructed connected fields of arbitrary characteristics. So if you take a non-zero characteristic, for example, 2 or any prime p, you will get a connected group of exponent p. So what they did, for example, Mutilin, he took the interval 0, 1 and turned every real into a variable. And the coefficients he took from a fixed field you desire of characteristic p or whatever, so that the field of rational functions is exactly what you need. So it is a direct sum of many copies of the group ZP, as many copies as the cardinality of continuum. All right. So let's see now the necessary condition to be virtually connected. This is a folklore lemma which says that a connected Tikhonov space that is not a singleton must have cardinality at least C. Let me explain you why this is true. In a Tikhonov space, you have a lot of real-valued functions. So in any space where you have a non-trivial, so if you have a non-constant real-valued function, the image is a subspace of the reals, a connected subspace of reals, but then it contains an interval. It is itself an interval, so it must have size exactly C. So let's call a group G, let's call it an M group if for every K, the subgroup of all K multiples of elements of this group is either trivial or has size at least C. So this definition is motivated by the lemma that comes here. It tells that virtually connected groups are M groups, and let's see why. So every virtually connected group is an M group, because if you take the multiplication by M, for example, then the image is still continuous. And if it is either trivial or has size C by this folklore lemma. Now, by using this term, Markov's problem can be formulated in a more concrete terms. So is every M group connected? In other words, is this necessary, trivially necessary condition also sufficient? Well, it turns out it is, but the proof is complicated. So the proof was divided in two cases. You call an abelian group bounded if there is a common exponent m for all elements. M times G is 0. Otherwise, the group is unbounded. So the problem was given in the case of bounded groups by Kirko in 90, and he proved that actually the bounded M groups are virtually connected, and this closed the case of bounded groups. Then we proved with Shakhmatov much later in 2016 that the same thing happens also in the non-bounded case, which was much harder. But our proof was using the Markov-Zariski topology of the group, and here I want to avoid this use and give an alternative proof that makes no use of Markov-Zariski topology. So let me say two words about this new proof. The new solution has two novelties. The second one is that Markov-Zariski topology will not appear, so let's forget about it right away. And the first is that we unify both cases, bounded and unbounded, and we give a single theorem that covers both. So this theorem uses, as I said, a function space. This is a group of G-valued functions defined in the interval 0, 1. This construction was first given in 1958 by Hartmann and Mitsiaski, and later independently by Dierov and Varken. So here comes the construction. Let G be any group. It can be also non-abelian. It's not important. And G to the I is the usual Cartesian power. So these are all possible functions from the interval to G. And for a fixed element of the group and for a fixed element of the interval T, G sub T will be the two-step partially constant function defined in this way. Let me define the graph of this function. It's a very easy graph, and it reminds the graph you saw yesterday in the first talk given by Professor Richard Aron. Let me consider the easiest possible. So here is G, here is T, 0, 1. So this reminds the graph of the interest function where times go. In the beginning, it's something like this, and it becomes 0. So this function will be used here. And if you take all possible functions with a fixed t but varying g, you obtain a subgroup. I will denote it by gt. This is all functions that are cut at the point P. Well, the Hartmann-Mitsielski group HMG is simply the group generated by all these functions. So what they generate simply all partially constant functions. So a generic element looks like this. You have T1 and some T2. And here comes the last Tn, and it becomes from this point on constant. So the usual piecewise constant function used so many times in analysis everywhere to define integrals and whatever. So this is our group. So what happens? This group algebraically is very simple because it is isomorphic to a direct sum of C many copies of the group G. So this is the lemma. So let's look at the topology. You may put also a topology on this group. For example, if G is a topological group, then the Hartmann-Mitsielski group G can be given a group topology, which makes it pathwise or arcwise connected in the following way. So use the usual Lebesgue measure, the usual standard probability measure on the interval, mu, and define the basic neighborhoods of this topology in this way. So for every neighborhood U of the identity element, neutral element in G, you define this set depending also on a positive epsilon, OU epsilon, all functions so that the set where they are non-trivial is measure less than epsilon. Let's take the simplest possible group you can have, G, the two-element group, Z2. So how this neighborhood looks like in this case, you have only one choice here, 1, 0. And you have some nodes here, T1, T2, T3, Tn. These are the nodes. Remember that the operation is modulo 2, so that you have either 0 or 1. You may have here 1, here 0, 1, 0, etc. Now you take the sum of those intervals where the function is non-zero, and you ask that this sum has measure less than epsilon. These are the members of your neighborhood. Okay. So we obtain a correspondence. Someone may prefer to call it a functor, but I don't want to use any category theory here. And so why this group is pathwise connected? Let me explain. It's very easy to see why it is. Okay. If you take the ends of all possible arcs or paths in your group, they form a subgroup that is the component, arcwise component of the zero. Since my group is generated by the elements GT, it is enough to show that there is an arc from 0 to GT. So you fix some GT you like, this one. Okay. Here is T. Here is the function GT. How to get an arc that goes from 0 to GT? You start by defining for every intermediate S the GS. So the family GS, when S varies from 0 to 2, is an arc that goes from 0 to GT. This is why this group is arcwise connected. So it is more than connected. All right. That it is divisible whenever G is divisible is clear because it is a direct sum of many copies of G. The other property is also interesting and very important, that if G is a dense subgroup, if D is a dense subgroup of G, then its Hart-Mitsielski group HMD is dense in the Hart-Mitsielski group of G. This we shall use. So let me give an example of a very easy class of M groups. It comes from the Hartmann-Mitsielski example. So let me give a definition. I call a group C homogeneous if it is isomorphic to a direct sum of C copies of itself. So obviously, if you have a C homogeneous group, then it is an M group, because if you take M times G, it is isomorphic to M times G taken direct some C many copies of it. So it is obvious that it is either 0 or at least C. So this corollary tells us that C homogeneous groups are virtually connected. And why they are? Because if it is C homogeneous, then it's isomorphic to the direct sum G to C. So it is nothing else but Hartmann-Michelski group of G. You can put on G the discrete topology just to have the easiest possible connected group. So in particular, if you take the cyclic group ZP, or if you want Z2, you get virtually connectedness for these groups. All right. Now let me recall the structure of bounded groups. A bounded abelian groups has a very special structure. Here happens something that doesn't happen very often. Namely, such a group is a direct sum of cyclic groups, many, many cyclic groups. And for every, you have a direct sum of this form. For finitely many primes, you can put together all p-torsion groups, so you obtain such a sum. And the cardinals that appear, alpha pi, they are usually called Ulm-Kaplansky invariants because they determine the group up to isomorphism. And leading ones are those that are the powers that correspond to the highest power of P. So the group is M group precisely when all leading Kaplansky variants are at least C. Now comes this notion of, okay, first let's say what is a variety of group. This is a class of groups stable under taking products, subgroups, and quotient groups. I will consider only the varieties, these varieties there. The variety the variety of all abelian groups, and the variety APN of those abelian groups of exponent P to the n. These are sufficient for this talk. So, three definitions. First, what is a cogenerator? A cogenerator for this variety is such a group I, so that for every non-zero element in any group G, you can find a homomorphism in this cogenerator that takes the fixed element to non-zero. This is equivalent and simpler to say that your group G is isomorphic to some power of this cogenerator. Now come V-injective. V-injective is injective in the usual sense, but with respect to this variety. So every homomorphism defined on a subgroup H of a group G can be extended to the whole group G. And finally, the V-injective hull is a group that contains your group G. It is it's essential subgroup, and it is V-injective. It is V-injective. So let's give it two examples to understand what it means. When V is the variety of all abelian groups, this is simply the notion injective is exactly as divisible. The injective hull is the usual divisible hull. And what happens to the other varieties, we will see in the next slide. In the next slide appears the injective cogenerators of the variety of all abelian groups of exponent P to the n. So take just any group I, P group. So let's see when it is an injective cogenerator. This is precisely equivalent to say that this I is a direct sum of many copies of Zp to the n. So it has the maximum possible exponent, and all all components coincide. So it's a very simple form. Well, as usual here, the rank, the free rank, and the p rank of the groups will appear as usually in the theory of abelian groups, and I will denote by spectrum, spec of V, all primes in case A is the variety of all abelian groups. Otherwise, it will be simply P. So here is the theorem, the principal theorem of construction of virtually connected groups. So what this theorem says? If you have a group G, and V, the variety generated by this group, what it means, if you have a group, you can generate a variety simply by taking all its powers, all subgroups of its powers, and all their quotient. This is already a variety. So V is the variety generated by G, and C is some topological group, which is a V injective cogenerator of V, such that G has size less than the P rank of C. And this for all primes that belong to the spectrum of this variety. Okay, if all this happens, then G will be virtually connected if G has a C homogeneous subgroup H, which admits a monomorphism in C with dense image. So let's see now how we can deduce the two known theorems in the bounded and the unbounded case from this general theorem. So let's see how the theorem of Kirchhoff, namely the bounded case, can be obtained from this general construction. Okay. As we saw, a bounded group can be written as a sum of finitely many primary components, and each one of them will be a P group. If G is an M group, every component GP will be an M group too. Then the leading Ulm-Kaplansky invariants of G. This happens because the Ulm-Kaplansky invariants of G are at least C. So this is just the leading Ulm-Kaplansky invariants. They are defined at the level of GP. You observe them in GP. So it is not restrictive to assume that G is simply a P group, so G is equal to GP. This simplifies the proof. Because when you succeed to prove it for GP, then the sum of finitely many virtually connected groups is obviously virtually connected. So let's fix a prime P, and let's call a group of this form a P group, a bounded P group. Let's call it an apex group if the leading Ulm-Kaplansky variant is at least C, so it is an M group, but all of them are less than C. So it's sufficient to prove the next lemma to obtain a proof of the theorem. So A, if G is a bounded P group, then, which is also an M group, as we have in the theorem, then G is a finite direct sum of apex groups. So we split into direct sum of apex group. B says that every apex group is virtually connected. And C, all bounded P groups having its leading Ulm-Kaplansky invariant bigger than equal to C is virtually connected. So let's prove this lemma now. The first A is simply an induction, simple induction. It's easy. So how to prove B? So you have an apex group and you want to see that it is virtually connected. So let's write it. It will have a leading part, which is the highest power, P to the n. This is H. And what remains is small. It has size less than C. This is important. We are going to apply theorem A, this general construction. How to apply the general construction? Well, we take a C, the power Zp to the n to K, to kappa. This is the same kappa that appears in H. H is a direct sum, but C is not a direct sum. It is a direct product. So it's a bigger group, a bigger cardinality. And K will be the Hartmann-Michelski group of C. So what happens is H, since H is dense in C, I can take in the theorem that I'm going to apply, I will take D equal to H. The density will be ensured. And pi will be simply the inclusion of H in C. So as D is a denser group of C, and since H is C homogeneous, the initial part of the hypothesis of the theorem is satisfied, so it remains only to check the last part. What is the last part? Here it comes. Yeah. The variety of groups generated by our group P is the variety of all abelian groups of exponent P to the n, where Zp to the n, as well as its power C, are injective cogenerators. And the P rank of C is to kappa, and this is bigger than the size of P. So now we can apply theorem A and claim that the group, it is not G, it must be P there. There is a misprint. This one is P. Okay, and now we are left with C. So let's recall what C was. We forgot what is C, maybe. At least I forgot. Here it comes. So all bounded P groups having all its Ulm-Kaplansky invariant bigger or equal to C are virtually connected. Okay, let's go and see. Well, this follows directly from A and B because we already proved it, and finite direct sum of virtually connected groups is virtually connected. Now remains the unbounded case of the theorem that we proved in 2016. Now we have a kind of alternative proof, but this proof follows that line. So I will go a bit faster here because it is already known. So here we use a notion that we introduced with Anna Giordano Bruno in 2003. So this notion is the following. You have a group G, and its divisible weight is simply the minimum of all possible cardinalities of n times G, where n varies over all non-zero integers. And the group is called W divisible when the divisible weight is equal to the cardinality. Well, this definition is inspired by the notion of divisible group, because a group is divisible exactly when it is equal to m times G for all. Here we don't ask equality of the groups, we ask equality of the cardinalities. Okay. Now this new cardinal we invented gives the possibility to simplify further the notion of M group. Here it is, an equivalent simpler form of M group. An unbounded group is an M group precisely when its divisible weight is bigger than or equal to C. So it's much simpler than before. And here comes a lemma we proved in 10 years ago. Every W divisible abelian group of size at least C contains a C homogeneous W divisible group H of the same size. Then we sharpened a lemma of Galindo and Macario. This lemma is a kind of decomposition lemma. So if you have a group of divisible weight bigger than or equal to C, then you have a decomposition of this G into a direct sum of two parts. N is bounded and it is C homogeneous. H is W divisible with the same cardinality and divisible weight as G itself. Now, another fact that was known before that, how look like the subgroups of the power of the torus, the dense subgroups, because every subgroup is emergible in a power of the torus, but the dense ones, they have some property, and here is the property. So, a group G, if satisfies these inequalities, so let's look at these inequalities. Its divisible weight is bigger than or equal to tau, and the size of G, which is of course bigger than or equal to the divisible weight, is less than 2 to 2 to tau, the double exponential of tau. Okay, if this happens, then G is isomorphic to a subgroup, important to a dense subgroup of the power torus to 2 to tau. Now, at this point, we can prove now the key step here is this proposition, again, 10 years ago. Every W divisible group of size, at least C, is virtually connected. In particular, every divisible group of size, at least C, is virtually connected. Here comes the proof. I prefer to skip this proof. It exists, so if someone asks, we can go back and see the proof here. Because now we are in the low part of the interest, so let's not exaggerate. So in the proof comes this is the proof of theorem A. Of course, it is again something technical that I will avoid and go to Appendix 2 instead. Because in Appendix 2, I will recall the original condition of Markov. I didn't give the condition M I was considering was not the original condition of Markov. I just noticed it when I was preparing my slides and tried to simplify the proof. So here comes the Markov's original definition, which was using the notion of unconditionally closed subgroups. And this, of course, is important and interesting, of course, but we don't have time now to go deeply in this issue because this notion using his condition is equivalent to our condition. So after all, it's nothing different. It is the same, but yeah, here comes the equivalence. The equivalence uses the Markov-Zariski topology. I don't think it is the case now to introduce explicitly, but this is a very important and very good, nice topology to study. It was introduced by Roger Brandt in '78 under the name verbal topology. Every abstract group has this topology. It is intrinsically put in every group topology, in every abstract group. So using this topology, one can establish that the both conditions are actually equivalent. And the last slide gives the example why Markov's conjecture fails and where it fails. It fails in the most non-abelian group. It is the group of permutation. If you take the reals, for example, and the groups of pole permutation of the reals, then in this group, it is an M group, but it is not virtually connected. And this is due to an interesting fact this group of permutation has. This group of permutation has a very nice pointwise convergence topology that all of us will ask, like, because it's very natural. It turns out that any other Hausdorff group topology on this group is finer than the topology of pointwise convergence. See, if there is any connected group topology there, then the topology of pointwise convergence must be connected. But it is not connected because it has as base of open neighborhoods of the identity these stabilizers, which are open, both open and closed. Yeah. This is it. I think I'll stop here and thank you for your attention.
All right. Thank you so much for the very interesting talk. Do we have any questions for the speaker? Yeah.
Thank you for the very interesting talk. I have a question about the first, about one of the first constructions that you showed at the beginning of your talk, when you constructed, you had the group and then the space of functions from I to the group, and then you relied on the Lebesgue measure in order to construct a group topology, and it looked okay. Yes. I mean that you were showing it, and it looked to me like that topology relying on the Lebesgue measure was something like outside of the real numbers, outside of the of an open U are have measure less than epsilon. That somehow reminds me of convergence topologies. Actually, there's a typical construction if you have a uniform space, and then if you have the set of functions from a given set to the uniform space, and if you have a Bornology on the initial set, then that Bornology induces a uniformity on the space of functions. In a similar way, you know, like mapping the sets of Bornology inside the entourages of the uniform space. So then if you start, so my question is, if you start with a topological group, then it is a uniform space, then you consider the set of functions from I to G. So, for example, if under certain conditions, the uniformity of the topological group induces a uniformity on the space of functions, and then the uniform under certain conditions, the uniform topology is also a group topology. For example, if you start off with a topological group, then it is that uniform topology in the space of functions is a group topology. So if those kind of topologies have been considered in any of these type of results, because that one, well, the problem maybe, like you said at the end of your talk, is that, for example, if the Bornology contains the finite subsets, then that the uniform topology is finer than the pointwise convergence topology, and then for example, connectivity and things like that, you lose that, like you said, but maybe some other Bornologies induce other group topologies, and maybe something else could be said on this kind of results. Or
You suggest to replace the interval by general domain.
yes.
If you do this, you may lose the connectedness, because connectedness is due to the connectedness of reals. These arcs are provided exactly by the arcs in the reals, first of all. Second, this group, as Varken and Dirov observed, they didn't know about Hartman and Michalski. They did the same construction with similar proof, but they didn't know. And they proved that the group is minimally almost periodic. This is completely different property, but again, it uses this specific property of the reals. But you're right that this is good to make this construction in general and then specify in all cases.
So I guess then, even if you keep the real interval, you use the connectivity, but then if you don't rely on Delibek measure, if you rely on other measure, then you probably also lose connectivity, right?
Mm-hmm.
Or
okay, yeah, thank you.
All right. Yeah, thank you. I mean, I'm sure people have questions, but we are out of time for this session, so I would like to welcome the next speaker. I'm sure Dikran will be available. Sure, yeah. All right, I would like to welcome the next speaker, Roger Buesco, who is going to talk about from positivity to the Riemann hypothesis notes on a personal journey.
Thanks.
Thank you.
Good morning, everyone. First of all, I would like to thank the organizers for this wonderful, wonderful meeting and its very heavy schedule of lectures. So I'm going to speak about something which, a line of research which occupied me for many years, and which is, in a sense, this is the right place to speak about it, because it is in the frontier between classical and modern analysis. So it all started, by positivity, I mean positive definiteness. It all started with a problem from colleagues from engineers, electrical engineers, who had some problem with an autocorrelation matrix, the positive definite, which then became a function. And they, of course, like all electrical engineers, were interested in taking the Fourier transform. So we solved that problem. And this sparked my interest on positive definite stuff. So the first thing was positive definite kernels, because we were dealing with kernels, which then led us to positive definite functions. And lastly, in the last few years, to what I call Laplace measure transitions. So this is the structure of the talk. And I'll start with positive definite kernels. So as I told you, this problem we had was basically, was essentially taking Fourier transforms of positive definite kernels. So what exactly are positive definite kernels? So first of all, let me define Moore matrices. Moore matrices are not matrices, they are functions. But basically, they are functions in which you do not assume any kind of regularity. I mean, the space may be any space you want to, but it has a property that any matrix, any square matrix which you form with a from that function is positive definite in that sense. So this is why they are called Moore matrices. Moore matrices have this very basic properties. So they are positive on the diagonal. They are Hermitian, and they satisfy this inequality. So the square of the value at each point, of the absolute value at each point, is less than or equal than the corresponding diagonal products. Of course, this is well defined because these are positive. Okay, so this is very easy property. So the next thing we had to do was to get into L2 setting. So this positivity condition is basically, we can replace it by that one in L2, and which is much more amenable in a sense to work with, especially if you are interested, of course, in Fourier transforms. Then what happens is, as Richard Aron yesterday told us, is that, I mean, there is an isometric isomorphism between that stuff and the corresponding operators. So we are going to look either at that condition or at the associated operators. So we call these kernels positive definite kernels, but also reproducing kernels, and I will speak about it later on. So we call it reproducing kernels for the moment. So for positive definite kernels, reproducing kernels, there is a very classical theorem on integral equations on bounded domains, which is Mercer's theorem. And Mercer's theorem basically tells you that you have this bilinear expansion. You have this bilinear expansion with positive eigenvalues. And now what we do, because we wanted to do Fourier transforms, we want to extend this to unbounded domains. And the unbounded domain case, this is a bit more delicate. You need some extra conditions, like you have to have continuity, actually uniform continuity, and that condition of the function tending to zero on the diagonal. But under these conditions, everything works wonderfully. So you have a kind of you have this bilinear expansion, and the corresponding operator is trace class. Everything converges wonderfully, and life is good. So this is what we have. In fact, we call this theorem extended Mercer because it extends Mercer's theorem to unbounded domains. So let me show you something very interesting. What makes this extended Mercer result work? Of course, if you have unbounded domains, you need an integrability condition at infinity. So what makes this extended Mercer work is that you have this, what I call this, let me just, no, okay, this diagonal dominance condition, which I pointed out at the outset. This is what this condition works as an integrability condition at infinity, because you have the absolute value of the function dominated by the diagonal. And so I call this, we call this diagonal dominance, sorry. And so this is what diagonal dominance means. I mean, if you have these 2 points in the plane, if you have these 2 points, xy, yx, By the way, the values at each of these are complex conjugate. What happens is that if you draw this square, then the product of these two is smaller or equal than the product of the two on the diagonal. And so this condition works wonderfully for integrability. Okay, good. So now suppose you want to study differentiable positive definite reproducing kernels. So this is for continuous kernels. You have this thing. What if you want to impose differentiability? Then what? What happens? Well, so what happens is wonderful. And by wonderful, I mean that, in fact, what happens is that this object, so we call Km this double cross derivative of K. So the kernel is supposed to be C2M, right? And if you take this derivative, this double derivative of the kernel, then that function Km is also a positive definite kernel, which is great. So, well, never mind about what I call Sn, S minus M. So basically, this is the following. This is C2 plus some uniform continuity stuff. So basically, you can think of Sn as being C2n. And so what you have here is that suppose you have a reproducing kernel in class S20, so C20. What happens is that all even order kernels of this type are positive definite, all of them, and up to C20, up to order 20. So this is great. This is very good because then we can apply the theory, the previous theory, and study these kernels. But of course, there is a problem because now we had an integrability condition, which is this diagonal dominance. And so now, what happens now? What happens is that you have, well, this result requires showing that this is positive definite. And what happens is that we proved. Oh, by the way, when I say almost all of the results are constructive, I mean using actually matrices and finite different matrices, and then making the difference tend to zero. So really constructive. And by this construction, we got an amazing, well, for me, it was remarkable, amazing at the time, family of inequalities, differential inequalities. So a different, a positive definite, differentiable positive definite kernel satisfies this, I don't know how to describe it, but this remarkable family of inequalities. So if you take the derivatives m1 plus m2 to the square at a point x, y, and square them, then this is less than or equal than the corresponding double derivatives m1, 2m1, 2m2 at the diagonal points. So this is, this was unexpected. But the great thing is that if you look at specifically at the diagonal terms, m1 equals m2 of this, then these become the integrability conditions you need. Actually, this is much more than the integrability conditions you need. This gives you a lot more inequalities. In fact, this is a kind of, this is really diagonal dominance, but on parameter space, M1, M2. If you look at those, at the parameters, what you are saying is that if you take M1, M2 and make the product of these two, then this is less than or equal than M1, M1 times M2, M2. So this is strange. What is going on here? I mean, this is great because it allows us to prove a lot of stuff, but for instance, let me just tell you, one application is that the eigenvalue asymptotics problem for positive definite kernels or for integral equations in general is a classical one. And eigenvalues of positive definite kernels in the compact case are very well studied. So this allowed us to study eigenvalue asymptotics for unbounded integral operators. So here you assume you have a CP kernel, and then what happens is that the eigenvalues go to 0 in this way, where P is the order of differentiability and beta is the rate at which the kernel tends to 0 at infinity. And so this is very good. I didn't prove this is optimal, but I'm sure it is optimal because it coincides with the optimal case in the compact case. So I'm sure it is. Without the beta, it is the well-known optimal case. Okay. Okay, so this is a great application, and we noticed that these inequalities are much more general than expected. For instance, they hold for holomorphic kernels in CN. So these are the corresponding inequalities for holomorphic kernels in several complex variables. So here you see the same thing, the same structure. I mean, this derivative M1, M2 is smaller or equal than the corresponding diagonal derivatives. So these are very, very robust inequalities. And they are so robust that, in fact, there's a whole other story, and this is the modern analysis part behind it. That story, this is why I call them reproducing kernels. That story is the reproducing kernel Hilbert space of Aronzine and Krein and so on. So what happens is that if you look more generally at positive definite kernels, you have this theory of Aronzine about reproducing kernels. So they have the reproducing property, and with the reproducing property, basically what you have here is you have these two abstract symbols, functions, if you want, ex, ey, and these define an inner product which is precisely k of xi. So if you remember that the first inequality, maybe I go back a bit. If you remember the first inequality, this one, okay. If you remember these properties, I mean, this is, if you look at this is Cauchy-Schwarz. This is really Cauchy-Schwarz because, you have positivity on the diagonal and you have the cross terms. So if this were a norm, then this is Cauchy-Schwarz. And what reproducing kernel Hilbert spaces say that it is really a norm and it is really an inner product. Okay. So this gave us a second way to prove these results, these inequalities. Okay, so now for my second part, positive definite functions. Positive definite functions are functions. Now we have functions from R to C, and basically they satisfy by definition this inequality. So this is, in fact, this is saying that f of x minus y is a positive definite kernel. So many of the results from positive definite kernels translate into this. And the translation of the basic properties is this one. So the function is positive at 0 and has a maximum, and Hermitian symmetry, and the last one. Okay, so positive definite functions are a classical object, very well studied, and you have the Bochner characterization, which tells you that a positive definite function is a continuous positive definite function is Fourier transform of a positive measure. Okay, a particular case, a special case, is where the measure is a probability measure. So basically, you normalize them. These are finite measures. So if you normalize, you have probability measures, and so you are speaking about characteristic functions. Okay, so let me tell you, I think I told you already, but we always prove this constructively, right? So sometimes we rediscover known things, sometimes we discover new things, and sometimes I'm not sure. Well, okay, so here we prove this, we use our inequalities, our family of inequalities to prove these two results. The first one is propagation of regularity, meaning that if you have a positive definite function, which is C2k in a neighborhood of the origin, then the regularity in the neighborhood of the origin propagates to the whole of R, which is quite remarkable if you think about it. But it only works for even order derivatives, not for odd order, just even order, which is the counterpart of this thing about the second derivatives, the even order derivatives of the kernels being positive definite. So this only works for, and well, you have this nice property that if some even order derivative at 0 is 0, then the positive definite function is constant. Okay, so now we have, these results in a sense are well known, these other ones. But now what we do is we take these results and say, okay, so you have propagation of regularity for positive definite functions. But positive definite functions generate a kernel. So maybe you have this property as well for kernels. And indeed you have. So if you have kernels in two variables, what happens is that now you need regularity along a neighborhood of the diagonal. But if you have this, then it extends to the whole space. So this is very nice. And this holds for these kinds of regularity. Continuity, C2n, or holomorphy, holomorphy in the complex case. So this is nice because you take the diagonal, you suppose in the neighborhood of the diagonal you have regularity, and then it extends everywhere. Again, this is done by constructively with matrices, with the Moore matrices. By the way, continuity was already known in classically. The propagation of continuity, the regularity, as far as I know, is an original result. Okay, we also prove some other stuff, some other interesting stuff, which I later realized was completely known from the literature, but again, our methods are matrix methods, which is the following. Suppose you have a positive definite function, an analytic positive definite function on the real line. So characteristic function, analytic characteristic function. In fact, it doesn't need to be analytic, just C infinity plus growth, which is not too large. So what happens? So if you have C infinity in the neighborhood of the origin plus that kind of growth, then C infinity extends to the whole real line. In fact, it becomes analytic, and then you have an analytic, real analytic function. And what happens is then that you can extend this function to a strip in the complex plane, and the strip, a maximal strip, and this maximal strip is bounded by poles. So positive definite functions have this great property. If they are analytic on the real axis, then they extend to a maximal strip, which is bounded by poles. Okay, this was already a well-known result. I mean, even from characteristic functions. And but again, we prove this, and as a kind of an epsilon result over there with matrices. And so when I say it was well known, what I mean is this. If you remember the Bochner characterization, so let me just go back to slides 3, 4. If you remember the Bochner characterization, so this gives you a characterization as a Fourier transform in R. Now, what happens is that if you have f of x analytic, real analytic, what you do is you just make the complex Fourier transform. So you stick a z instead of an x. And this extends, it can be shown that this really extends to the complex plane in the same, in the way I was describing. So you have, this gives you, this representation gives you the analytic extension to a maximal strip bounded by poles. Now this is a theorem. This is very good because now you can work with an explicit expression for f of z. By the way, typically, I mean, this is the direct thing, but typically what we want to do is we want to rotate this 90 degrees. And to rotate it, we say for a function g, we take f of I z, which is just putting an extra I on the exponential, and then what you get here is the bilateral Laplace transform, of course. So in fact, we are going to work with these objects, which are bilateral Laplace transforms of measures, of positive measures by the Bochner theorem. And now we rotate everything 90 degrees, so now we have a vertical strip bounded by poles. Sometimes we call these co-positive definite functions, but I'll drop the co and somewhat abusively call them positive definite as well. Okay, not very important. So what you have is this. For positive definite functions, holomorphic positive definite functions, what you have is this. Here on the real axis, you have, oh, by the way, this is what I'm going to say is we rediscovered this result and we realized that it is periodically being rediscovered by different communities. So what you have, if you have a positive definite function on its maximal strip, so what you have here on the real axis is a characteristic function. So a Fourier transform of a probability measure. I mean, normalizing, you can always have a probability measure. And so this is very interesting. You have a probability measure. Here on the real axis is the characteristic function. And here on the vertical axis is the moment generating function. So this function f of z tells you everything about the probability distribution. On the real axis, it gives you the characteristic function, and on the imaginary axis, it gives you the moment generating function. And in fact, so this is well known. That part was well known. Now, what we did was to apply our inequalities to this, to this setting. And in this setting, what you have is a very curious thing. I don't know, I'm no probabilist, so I'm not sure how much of this is known. But what you do is, I mean, in each horizontal line, so this is on the real axis, you have the original characteristic function. In each horizontal axis, you have another measure, because I mean these measures are connected by the Laplace integral to each other. And so in each horizontal line, you have a probability measure, the characteristic function of another probability measure. So what happens is that each of these probability characteristics functions are related to each other because they are tied together by the Laplace. And then what happens is that the shape our inequalities take in this setting is that if you take y and y plus beta, y minus beta, you have this, the moments relative to the measure mu y satisfy this inequality with respect to the measures y minus beta, y plus beta. Again, I'm not sure how much of this is known. Specializing here to y equals 0, so to the original mu0, to the original probability distribution, you have this inequality relating the mu0 with mu beta, mu minus beta. And finally, specializing again to beta equals 0, what you have here, what you have is this measure, the moment satisfy this. This is trivial. This is trivial because this is the Cauchy-Schwarz inequality for integrals. Okay, so at least the last one is absolutely trivial. I'm not sure about the previous ones. Okay. Okay, so now we're getting to where things get really interesting. Measure transitions. Okay, so now we're going to rotate this everything 90 degrees and get the Laplace representation. So now we are speaking about vertical strips bounded by poles. So what happens is the following, is that you have, this is in a sense more or less classical from the Laplace transforms. You have maximal vertical strips bounded by poles. For instance, if you have here the gamma function, you have a representation, a Laplace representation on the right half plane, where the function is positive definite. That's what the plus sign means there. And then you have a pole. And then on the other side, on the left side, you have a strip in which the function, the gamma function, is negative definite. And then you have another pole, and it switches polarity again. Polarity, I mean, from negative to positive again. And so on, and so on, and so on. So you have an infinity of poles at the integers, at the negative integers, and in each time you cross a pole, you switch polarity. Okay, so when I first look into this, oh, this is nice. So this means that you have a positive definite function. This always happens. So you get into a pole and that's not true. That it is much more complicated than that. Because, for instance, you have here the zeta function. For the zeta function, you have of course a pole at z equal 1. Here on this side, it is positive definite. I mean, positive definite rotated, right? Rotated positive definite, which means that on each vertical line, it is a positive definite function. But then, when you hit the pole, on the other side, you have nothing. You don't have positive, neither definite, negative, nothing, from the point of view of polarity. So the polarity, so to speak, dies when you hit this pole. And even more interesting, if you consider this kind of modified zeta, if you take zeta divided by z, then what you have is it is positive definite here on this strip. Then you have this pole. Here it becomes negative definite. And then you have another pole at 0, of course. And on the other side, then you have nothing. So this is delicate. This is delicate. So our naive ideas about switching polarity as soon as you hit a pole are not true, because you can really lose polarity. So what is going on? Well, this was a puzzling problem for a lot of time. So given we have two related problems, which is when you have this setting, what determines whether or not when you hit a pole there is some representation on the other side? You may have one, you may not have one. And in the second case, in the second point, in case such a representation exists, what can you say about the corresponding measures? I mean, they are represented by two different measures. And so how are they related? And this is what I call the measure transition problem. There were tangential approaches to this by Van der Poel and Wither in the 20s and 40s. So to deal with the first problem, we try to simplify it in the sense, okay, I'm not yet completely sure what happens when you lose polarity. I have a pretty good idea, but I don't have a characterization yet. So what I'm going to suppose is that is that you have, in fact, two different representations with a pole in the middle, a separatrix with one pole. Okay, so, and in this setting, what you have is that, so you have one representation on the right, another one on the left, and what happens is that the representations are, the measures are, these are the densities. The densities are related by this, by a polynomial times e to the minus ct. C is the, well, is the exponential which comes from the Laplace. So e to the c is the translation. So this represents the abscissa of the separatrix, and this polynomial is basically a polynomial on whose coefficients are the coefficients of the Laurent expansion of the pole. Right? So this is a very clean result, because you have this transition polynomial times an exponential, which gives you tells you where the transition is happening. A very clean thing. Okay, so this is where things stood about 5 or 6 years ago, and then we had this problem. We had these delicate problems. What is the behavior of a measure as it approaches the boundary, the separatrix? I mean, when a measure is going here, what really happens? What is happening to the measure? I mean, if you have a pole here, of course, the Laplace integral must explode. It cannot be defined. But now, suppose you remove the pole, you take out the principal part of the function. So now it now becomes a problem in holomorphic functions. You have holomorphic functions. You have a holomorphic function. Now you've taken away the principal part. This is all holomorphic, and you have two neighboring strips, in which there is a Laplace representation here and a Laplace representation here. So So the first question is, notice that when you take away the singularity, you lose positive definiteness, definitely. So now you are talking about a problem about complex analysis, really. And the question is, can you have this? Can you have a holomorphic function here on the whole of this, such that you have a Laplace representation on the right, a Laplace representation on the left, and they are different, without having any poles? And this is a haunting problem, because we take the separatrix to lie at c equals 0. This is a very, very difficult problem, more difficult than I thought. It is like, I call it a ghost transition, because it seems like, okay, it's clear what happens when you have positive definiteness and you have a pole. The pole makes it impossible to go through. But now if you take away the pole, it's as if the remaining function remembers that there used to be a pole over there. So it's a kind of a ghost. That's why we call these ghost transitions. And of course, the problem is we don't know if they happen, if they are real, if they happen. In fact, the best result here, the best result we had was from Harper, who proved that it is possible for a function to have two different Laplace representation in closed strips, but not adjacent. So you always have to have a non-zero gap in which there is no representation. It is a very curious result. He does this with 5 minutes. 5 minutes, okay? Yeah, okay. Using the Newman function, which is an entire function bounded on every line, on every ray. Okay, so this is what was known. So our question has no real answer until João Fontinha, who is speaking tomorrow, came along, and he showed that ghost transition. I mean, she showed two things. First of all, if if you have a bounded growth condition, a very large growth condition on vertical lines like that, the Fragment-Lindelof condition, then you cannot have ghosts. This is true for instance, for the zeta function, many functions, because this, if you look at this, this is an incredibly rapid growth. Okay, so and you have transition formula. These are a bit more complicated because these have finitely many poles. This is for infinitely many poles, but basically you have this kind of transition formula, so we can relate what happens in. And then, even more interesting, João proved that ghosts exist. Ghosts exist. So this strange transition in which you have two different representations in an adjacent strip with a separatrix without singularities, this may really happen. Of course, it requires violating the Fragment-Lindelof condition, but of course, and he constructs a function, a very strange entire function, which does this. And basically, this function is a function which is bounded on any. Please correct me if I'm wrong. Bounded on every vertical line, except at imaginary axis in which it grows super exponentially, and it is entire. Is that correct? Okay, so he'll speak about that in tomorrow. Okay, so I'm reaching the end of my talk. So what are we going to do in the future? First of all, we would like to find optimal bounds for these no-ghost transitions. We have sufficient conditions which are Fragment-Lindelof. We have a counterexample which is miles away from Fragment-Lindelof, but it would be nice to have optimal bounds. Then we have this question of characterizing exactly what happens when a bad measure approaches a separatrix. I have a pretty good idea of what happens. I mean, you get a signed measure which oscillates very, very widely, very, very widely, each exponentially widely, in fact, in most cases. And so you may have simple convergence on the separatrix, but not more than that. And certainly you can have the representation may die there. Then Fontinha will also speak tomorrow on the connections with PDEs, namely parabolic PDEs, because his counterexample gives also provides a counterexample for the uniqueness of heat equation. And finally, the Riemann function, the Riemann hypothesis. Okay, so if you, as I told you, the zeta function and the Riemann hypothesis is somewhere around here because you have these representations for the zeta function. Of course, then you are interested in the zeros, not the poles. But what you can do, for instance, is take the inverse of the zeta function, which transforms zeros into poles, and now you are in a setting which may allow something to be said. I mean, this is the Mertens function, which has this Mellin transform, or equivalently that Laplace transform, and so of course the representation dies at s equals 1. The separatrix is at s equals 1, and then on the other side, what happens on the other side? I'm okay. 100% sure that you have no Laplace representation on the other side. Okay, so I won't be able to say anything really meaningful. But if we find ways of characterizing what happened in point 2, characterizing what happens approaching a bad separatrix, maybe you can say something about this. I mean, remember, just pushing the separatrix by epsilon, or showing that there is a very thin strip on the other side of s equals 1, would mean that there are no zeros of the Riemann zeta function there. I'm not saying that we will do that, but it may happen that we may be able to say something about this. Okay, so this is, okay, so this is what I had to tell you, and thank you.
Thank you so much for the haunting talk. Do you have any questions for the speaker?
I think it's absolutely fascinating. And I'd like to ask now about the big picture, not just one separatrix, but the entire space. This gamma function, for example, which is so beautiful, is it rather an exception? Is it rather a typical case? What do you expect as a big picture? What are the conditions you suppose that make it look beautiful or to make it die? Thank you.
Yeah, I mean, the great thing about it really depends on the defining measure. Let me just check the gamma function. Oh, I don't have it here. Okay, never mind. So what the real important thing is the defining measure. So the gamma function may be written in this way. I mean, just making small changes of variable. The measure, here the measure is, okay, let's put it this way. This measure is e to the minus e to the t. So what happens is this measure extremely well behaved. Yeah. So it is so well behaved that every time you make a crossing there, what happens is that in the exponential part, you take away the first term of the exponential, and everything else also behaves well and converges and so on. And actually, because this is an alternating series, this is what happens when you take the first term, which is positive, you get the first term, the new first term is negative, and so on. And so this is why you have this alternating thing. For the other functions, the measures are much more complicated. I mean, for instance, for the zeta function, these are a sequence of Dirac measures, and so it really explodes when you get to when you approach the separatrix. So you have nothing on the other side. I think I can understand that, but I still don't have precise results. So for the moment, I would just say that this measure is extremely well behaved and everything is great.
Okay, I'll allow for maybe one more question.
Good morning. Thank you so much for your presentation. Actually, my question is very basic. This year, my lecture were dealing with Lebesgue theory, so that was a nightmare. So the definition 3 of your, I don't remember the name, sorry, so the definition
one,
3.
sorry?
The definition 3, yes. Definition 3.
Definition 3.
Yeah, the formula 3. Yeah, the very basic definition.
Would that be
yeah.
the positive definite function?
Yes, the very basic definition.
Yes.
3.
3.
Yes, sir. 5.
3. Was it in kernels?
Yes.
Oh, I'm sorry.
Oh, it's okay. I cannot see.
Okay.
This is very stupid as a question, but I cannot see why the integral is convergent.
Let me just check.
Yes, this one.
Okay. Okay. Yes.
I cannot see why the integral is convergent.
The integral?
Yes.
Because everything is L2.
Yes. Phi is in L2?
Yes, phi is in L2. Yeah, phi is in L2. So everything is L2. This is basically the L2 version of the Moore matrices. Yeah, it works because everything is L2.
But you need some decreasing for for the function key.
Sorry?
Cauchy-Schwarz?
Ah, Cauchy-Schwarz. Yes,
Okay.
yes, yes. Oh, yes, sorry. Cauchy-Schwarz. Yeah, yeah.
Okay. Double it. Okay. Okay. Thank
Yeah.
you. Okay.
Yeah,
Okay.
yeah,
Thank you.
yeah. That's it.
All right, let's thank the speaker one more time. So our last speaker for this session is Sergio Ahmad, who is going to talk about variational problems depending on non-local, non-singular operators, applications to integral equations. Thank you.
I put the first day, but I have also here.
I think they're just fixing the files, maybe a minute or so.
Okay. Thank you very much for coming, and thanks to the organizer for giving me the opportunity to be here. This is a joint work with my colleagues, Pablo Predregal from University of Castilla-La Mancha, and me from University Polytechnic of Cartagena, both in Spain. In this talk, we will work about some variational framework in order to study non-local operators and the application of this general framework to integral equations. Okay, this is the outline of my talk. We'll start with a motivation, in particular the relation of some non-local models in particular interested problems and the relation with integral equations. Then we will present our general variational framework that include, as a particular case, integral equations. For the theoretical part of the talk, we have to distinguish some properties on the functional and in particular compact or continuous and linear and nonlinear operators, because we need different variational tools in order to prove the theorems. In a natural way, from the variational framework, we derive a variational numerical approach, and we make a comparison with classical scheme like Picard iterative method. And the main advantage of our variational approach is that the convergence is global. But normally in iterative method, all the iterative method, Newton method and so on, always the convergence is local. We need an initial guess close enough to the solution in order to ensure the convergence, in particular to the solution of the integral equation. In our approach, this is not a problem because our functional only will have a minimum, and then the convergence will be global. This is the most important thing. Finally, some conclusion and future works. Okay, there are many interesting problems in relativity transfer, population dynamic, neural networks, no-local diffusion, image processing, where no local operators appear. And in most of them also appear the solution of integral equations. Okay, we start with the integral equations, then we define the operator T. This is the non-local operator, the integral part. And with this definition, we can write in a compact form the integral equation like this. And then, in a natural way, we define the residual. And this is the way to apply iterative method to approximate integral equation, because this is nothing else that the residual equal to 0. Now we change this. We consider the residual, but not anymore equal to 0. We like to measure the L2 norm of the residual, like this, and then we define this functional. And then the minimum of this functional will be related with the solution. In fact, the only minimum of the functional will be the solution. Then solving the integral equation is equivalent to minimizing this functional until the functional go to 0, okay? In previous works, we make similar ideas for other type of equation, differential equation, stochastic differential equation, and today is for integral equation. Okay. The general framework that we propose is like this. We like to minimize a functional like this with double U, an operator here with 3 components, and this is a general case. And in the particular case that capital W is defined by this expression, then we recover the error functional of the beginning. Then it's a particular case of this general framework. Okay. We consider variational functional, then the goals that we will have are these 3 ones. The first one is the existence of minimizers of this operator, optimality condition in order to obtain condition of the solution, and also some numerical algorithms, and try that the numerical algorithms give something better than the classical approach, in this case, for the solution of nonlinear integral equation. Okay, different types of operators we will consider, because as I said at the beginning, we need different variational tools in order to prove these goals. In particular, we have these 3 cases, and I would like to present several examples of these cases. The first one, the linear and compact case. For instance, the Hilbert-Smith operators on the inverse Laplacian operator are particular cases of this. The Hilbert-Smith operator, I define it by some kernel with in L2, and an operator T with multiplying by this kernel, and this operator is linear and compact. This is an example of this. The other one, the inverse of the Laplacian, also in L2. When we have a function f, we assign u, where the Laplacian of u is f, and u belong in the Sobolev space H01. And here is compact because we have that this Sobolev space is a subset embedding into the LP space. For linear, continuous, and non-compact in general, for instance, convolution operator that appear in image processing in many problems, where K is an L1 kernel, and the operator T in LP for any P. This is an example of linear and continuous. Another example is the gradient version of the inverse of the Laplacian. Here, the only difference at the beginning, at the first example, this is the assignation. Here, the assignation is the gradient of the function. Here, we have continuity, but no, the operator is not compact. For instance, nonlinear case, but compact for a composition of a Carathéodory function with a T0, a compact linear operator. This is an example where it's not linear, but still compact. And the general case, an operator that at the beginning that appear in nonlinear integral equation. Typically will be nonlinear, continuous, but not compact, okay? what is the main assumption that we need in order to study variational problem? This is the main assumption: coercivity, continuity, and convexity. Why? Because in variational problems, if we are able to do, one method is the Dirac method of the calculus of variation. What is the Dirac method of the calculus of variation? The key steps are the following. We have an energy functional here. The first thing is to find a bounded minimizing sequence. That means that we have that the limit go to the infimum of the energy functional. Then, using coercivity and compactness, we can extract a subsequent convergent weakly. And then we use the lower semi-continuity to have this inequality. And using all the steps, we arrive to the system of the minimizer. This is classical in the calculus of variation. And if we are able, we try to use this in our theorem. But this will be true for the first examples in the linear case, but in the nonlinear case, we will have to change the strategy. Okay, this is the theorem for the compact case. Okay, we have compactness on the operator T, and we assume coercivity, continuity, and convexity on W. Then, if there is a function in L2 with the operator, the functional is smaller than infinity, then the variational problem has a minimizer. And if the convexity is strictly, then the minimizer is unique. And the proof of this is a direct application of the Dirac method of the calculus of variation. If also we have this quadratic growth in W and some regularity in order to take derivatives, and we denote T start the adjoint of the operator T, this is the optimality condition of the minimizer. And this is only make the derivatives and see what is the optimal condition. As a corollary, we have the case of linear, not compact, but linear. It's a corollary because we can use the Dirac method but with a little chain. What is the chain, or what is the hypothesis, the extra hypothesis is that the convexity and coercivity is not only in the first variable, but in both variables. With this little change, we can use the Dirac method of the calculus of variation in order to have also the results. Okay, this is because in the compact case from here, we can obtain the strong convergence, but here, only with continuity, we have weak convergence, but using that we have convexity and coercivity in both variables, we are able to find the theorem. And also, we have another corollary in the case of the linear theory for integral equations, but are linear. We obtain that this equation have a unique solution, that this is classical, but it's a corollary of the general variational framework that we present. What happened in the nonlinear case? Now, change all, because we lose two things. First, the convexity structure is losing, and the weak lower semi-continuity. Then we cannot apply the Dirac method of calculus of variation, and we need a different approach. And here we will consider is new, not new, recent. That is the error functional approach that was presented some years ago by my collaborator Pablo Pedregal. Okay, I will explain what means this. Okay, first a definition. A non-negative seg1 functional E in a Hilbert space, an error functional, if verify these two conditions. The first one is for any bounded sequence that we have that derivative goes to 0, thus imply that the functional go to 0 also. And also we have this type of coercivity. Any difference of elements of H are bounded, but the value of this of the functional in this element, the sum of this value. With this coercivity and the first one, we will be able to prove this general theorem that say that if E is an error functional, then there is a minimizer such that the error goes to 0, and also we have this stability property. The idea of the sketch of the proof, first is the construction of a bounded minimizing sequence. We denote by M the infimum, and then we choose a minimizing sequences converging to M. We have these properties in mind that we will use later. By this property, the sequence is bounded. Then, using the Eklund variational principle, we can extract a subsequence that verifies this property, and then using the first property of the error functional implies that this sequence go to 0, and then we arrive that M is equal to 0, and the infimum is 0. This is the first thing that we need to prove. Also, the existence of minimizer. For the coercivity property, we have this bound, and this go to 0. Then this sequence is a Cauchy sequence, and then we have that the sequence is convergent, and also it converges to 0. And finally, the uniqueness and stability. If we have two points in the Hilbert space that the functional is 0, by the coercivity, we start trivially that are the same, and also using this property, we have the stability, this stability property. Okay, this is a main result that we can try to use instead of the direct method of the calculus of barrier. And this is for the nonlinear case, our theorem. We assume two technical hypotheses, that the partial derivative of k, the norm, is smaller than a given function, and the integral of power 2 of k is smaller than this quantity. Then, with these two technical hypotheses and regularity of the kernel, we have this nonlinear equation admit a unique solution in L2, and also we have this stability bound. For the sketch of the proof of this theorem, we start with our error functional. We try to see that this error functional verifies the two hypotheses of the general theorem. Then the first one is what happens when the derivative goes to 0 if the functional goes to 0. We take the derivative, the directional derivative, and give this expression. This is the residual as before. And then we consider this part from here. Okay? And this is B. And for a fixed U, we try to solve this for B. This here is where appear the two technical hypotheses, because the two technical hypotheses, with these two technical hypotheses, it's possible to verify that the previous linear operator is invertible, and then we can choose this solution, this B. Choosing this, we arrive that this one is 2 times the error. Then this implies directly that the image throughout the functional goes also to 0. And the second thing, the coercivity, we consider U minus B. We put this classically. We take norm, arrive here, and then we use two things. The first one, Lipschitz continuity of the kernel, and also the Jensen inequality to bound the third part, and then we arrive to the second property that we need to apply our general theorem. Then we have both hypotheses. Then using the abstract theorem, we arrive that exists a unique solution in L2 such that the value of the functional is 0. That means a solution of the nonlinear integral equation. Okay, now the numerical strategy. We have first two possibilities. The first one is make first a discretization of the integral and then using the variational strategy, or the second one, that is the one that I will show you now, is first derive the continuous descent method and then discretize. And this, in our experience with other type of equation, is the best one of the two options. We compare in the numerical experiment our variational approach with the Picard iterative method. In both cases, I will use the Nixtron discretization with n quadrature node and weight 1/n. Okay, for the convergence hypothesis, Picard, everybody know, is converging if we have contraction. And contraction is a particular case, or contractivity is a particular case of our properties. Our variational framework use the restriction of the hypothesis are fewer than contractivity. Okay, we will present 4 samples, 2 in 1D and 2 in 2D. This is the first one with a localized nonlinearity. Here, AX is around 0, and this is the nonlinearity. And, sorry, we consider as initial case U0 = 3. We are not, in this case, in a contractivity region for Picard, but in any way, Picard converge. This is the residual that you can see in 5 iterations goes to E10-7. Is quite good. Here is the comparison with our variational framework. Is more or less similar. We, after no 5, but 4 iterations, we obtain this one. This is for 3 iterations, more or less, the case of Picard. Then seems that the variational approach converges with a small number of iterations. This is the second example. It's a cubic nonlinearity with an oscillatory kernel. And we consider 2 cases. The first case is initial guess 0, 1. In this case, we can prove contractivity. We have contractivity, and we are inside the hypothesis that need Picard iteration. And then we obtain a very good result with Picard. But here, if we go a little far from that, and here we don't have contraction, then Picard iteration is not convergent. Okay, this is the case outside the contractivity region that the variational method gives. After 4 iterations, we have this value of the residual, and we don't have this restriction to start with points close enough to the solution. Now we go to the experiment. Here is also a localized nonlinearity in these disks with this radius. And this is the result. More or less is the same as in 1D. Both schemes are converging, but here with few iterations we obtain an error much smaller. And the final example is a separable nonlinear Urysohn equations with this value of A and B with sinus. And we have this. For Picard, we obtain convergence, but we start to obtain something reasonable after 1,000 iterations. But in the variational problem that I say several times that we have a global convergence. With 6 iteration, we obtain a good result. Okay. Some observation, Picard, and the same type of result we can obtain with Newton method or other iterative method, because all iterative method need initial guess close to the solution. All these iterative methods are local convergence. Then this is a problem, because in many problems we don't have a priori estimation of where the solution is. But in our variational error functional approach, the main advantage is the global convergence. Also for a variational calculus framework or something, it's interesting, the theoretical part also, because normally people use the direct method, and now here it's not possible, then also it's interesting. Okay, and we observe also faster convergence with a number smaller the iteration we obtain, the residual is smaller. Okay, conclusion, we have presented a unified variational framework for non-local operators, and we use this for integral equation. In the linear case, we use the direct method, and we obtain an optimality system. In the nonlinear integral equation, we need to consider error functional. It's a new view. And the numerical scheme inaugurate the global convergence from variational structure. I would like to thank Professor Semyon, because in our last meeting, during the question, proposed me the consideration of integral equation in this general framework. Okay, and as future works, we have 3 that are more or less independent, are close, because are future from the work of today, but are independent. One is time-dependent models, the use of derivative with t, and see what happens. Constrained systems, and integral differential equation, where we combine local and non-local operators, is another interesting problem for us. Thank you very much for your attention.
Thank you, Sergio, for the talk. Any questions from the audience? All right, we have plenty of time.
Thank you.
So I can leave everyone to just think about the questions. Just joking.
Thank you.
But if there are no questions, let's thank the speaker one more time. Okay, I think now there's a coffee break, but it's...
Okay, today the coffee break is a takeaway, because there is a bag with just a bottle of water for a trip to Pompeii and something to eat. So collect it then. The bus will depart at 2 o'clock from Palazzo di Città for Pompeii, and there is a Paco, switch. Okay.
There's a switch of rooms. Parallel session A is there, parallel session B is here, and parallel session A was originally appointed for the Cagliari people, but then they moved here, and then the other people moved to parallel session A. Okay, it's a mess. I know. Okay, that's all. Thank you.
6, 6, 6, 6. Questo è troppo alto.
E poi lo regolo mano.
Ok.
A seconda.
Non c'è nessuno, vi ho detto. Meglio. Ti fa la domanda il ragazzo del tecnico. Non
Passiamo poi in italiano.
6. Si inizia con il talk. Good afternoon, everyone. Welcome to this session. It's my pleasure to chair this part of this conference. Now we have 3 speakers. Let us start with Professor Alessandro Colombo, and his title of the talk is Boundedness in a Class of Keller-Segel Models with Dissipative Gradient Terms. Please welcome.
Thank you very much, Gamze, for this nice introduction. Yes. Thank you very much to the organizers that are not here, that I cannot thank for inviting me here. And I will speak about some chemotaxis models and some conditions for the boundedness of the solution. This is an image of the chemotaxis phenomenon at the microscope. We can see that we have a biological distribution, that it is initially homogeneously distributed all over the domain. And over time, this distribution, we can see that the cells begins to aggregate in one point of the domain. And at a certain time, we can have what is called the blow-up. The blow-up is an uncontrolled aggregation of the cells of the distribution. This is one of the most general models that describe this phenomenon. We have U, that is the distribution of the biological material. We have V, that it is the distribution of the chemical signal, and also W, but V is an attractive signal, a chemical substance that induce an attractive movement towards this chemical gradient, and W instead is a repulsive chemical signal. The first, we have a system of coupled differential equation. The first one, it tells us how the distribution of the biological material changes over time. We have the function D, that is the models the diffusion of the cells, the function S that models the reactivity to the attractive chemical signal, and the function T that models the reactivity to the repulsive chemical signal. And also the function H that it is the logistic source. So tells us how over time in the domain the cells grows and dies at a certain time and in a certain point of the domain. The fourth equation represents the Neumann, homogeneous Neumann boundary condition. So we have a system that it is completely isolated. And the last are the initial distribution, so at the time t equal 0. We have tau that can be 0 and 1 if the system is parabolic elliptic or fully parabolic. We have a solution that can be globally bounded, so we have that Tmax is infinite and the solution is bounded in the L infinity norm. We have a solution that can be unbounded in finite time, so the Tmax can be finite, but the solution is unbounded in the L infinity norm as T approaches to Tmax. And a third type of solution, the solution can be unbounded in infinite time. So we have the Tmax is infinite and the superior limit as T approaches to Tmax is infinite as well. And this is the first model of the chemotaxis, one of the first models that has been studied precisely by Keller and Siegel. We have no repulsive signal, we have only the attractive signal, no logistic source, and linear diffusion and linear sensitivity for the attractivity. And the signal is produced linearly by the cells. How we can see in the second equation, the term plus U in the second equation tells exactly that it is produced by the cell themselves. It is proven that if this number, k times the initial mass, is lower than the number 4 pi, all the solutions are globally unbounded for all initial data. And for this initial data, if this number is lower than 4 pi, and if this number is greater than 4 pi, for some initial data, the solution may blow up. The counterpart is the consumption model. The first equation is the same, linear diffusion, linear sensitivity, but the signal here is consumed rather than produced. And here for 1 or 2 dimension, the solutions are global and bounded in general, but for dimensions greater than 2, solution maybe can be unbounded. It is not proven yet, but it is, let's say, very difficult to see a solution that blows up because the signal here is consumed. And let's talk about the logistic term. This is one of the first appearance of the gradient term in a logistic source. We can have in this equation the distribution U. The first equation is ut equal Laplacian U, so the natural diffusion, plus U to the raw power, so the natural births of the cells, minus U, the natural deaths of the cells, and minus absolute value of gradient of U to the gamma power. This is what is called accidental deaths. This is because this was introduced by Soufflet in this case because in a situation where we have predator-prey systems, we have that when the cells move in the domain and the velocity of the diffusion is too high, the cells cannot avoid the predators anymore. So this is what it has been interpreted like accidental deaths. It is proven that if this exponent gamma is lower than the exponent of the natural birds, then the solution may blow up for some initial data. Instead, if the exponent gamma is greater or equal than rho, it was proven by Quittner that all the solutions for all initial data are global and bounded. And this idea was recently applied by Ishida, Lancaite, and Villaloro. They proved that in a only attractive version of the model, with the linear production of the chemicals attractive signal, they proved that the solution is always bounded if this exponent gamma for a logistic lambda u to the rho minus me u to the k minus c gradient of u to the gamma power, solution is bounded if gamma is in this interval here that depends on the dimension of the system. Note that gamma here has to be less or equal than 2. We will see later because of why has to be lower than 2. And these are our results. The first one is in collaboration with Tongxin Li, Daniel Acosta Soba, and my supervisor at the PhD, Giuseppe Villaloro. We study a completely nonlinear, attractive, repulsive system with the logistic in the exact form of the other article by Ishida, Lancaite, and Villaloro, lambda u to the rho minus me u to the k minus c gradient of u to the gamma power. The first and the second equation are respectively for the attractive signal and repulsive signal, and we have nonlinear production for the two signals. And we have proved that the solution is bounded in the parabolic elliptic case if gamma is between n over n plus 1 times m2 plus alpha, or 1 if 1 is greater than the other number, and gamma is to be lower than 2. Or in the fully parabolic case, unfortunately, we have to bound also the repulsive part, just because of some problems in the calculations. Maybe this can be avoided in other case. We don't know, we have to think about, but for us in the calculations, the parabolic, for the parabolic elliptic case, the interval of gamma can be larger. And if we put m1 equal m2 equal alpha equal 1, and we get rid of the repulsive part, so the linearization of our problem coincides with the problem studied by Ishida, Lancaite, and Villaloro. And we find exactly the same interval they found. So we have an extension, we studied an extension of their work. Another result, I try to apply this idea to a consumption model, only attraction model, but with the signal that it is consumed by the cells. And I found that if gamma is in the same interval as before, 2n over n plus 1 and 2, or if gamma is exactly equal to 2n over n plus 1, so the limit case, If this inequality is complied, is satisfied, and in this inequality appear the initial mass, numbers that depends on the coefficient of the logistic, the dimension of the problem, the sensitivity, the coefficient of the sensitivity, and the norm of the initial distribution of the chemical signal, then the solution is bounded. This, instead, in collaboration with my supervisor and Daniel Acosta-Soba, this is the nonlinear version of the previous model. So in the previous model, we have linear diffusion and linear sensitivity. In this one, we have nonlinear diffusion and nonlinear sensitivity. So we try to extend the previous result, and we find this one. So because of the sensitivity and the diffusion is nonlinear, here gamma has to work a little bit more because gamma has to bound also a term that depends on the rates of the chemical sensitivity. So we proved, first of all, we proved that the solution exists in a certain time, 0, capital T. And we try to extend this capital T to a certain time, T max, the maximum time of existence, until a point that T max can be infinity, so we can extend this capital T a lot of times by iteration, and this capital T in the end can be infinity, or we reach a point that we cannot extend this capital T anymore, and we reach a point that T max is finite. We cannot extend it anymore. And in this case, the C2 plus delta norm does not exist anymore at this finite time. So if we want to transform this criterion with the norms in L infinity, then gamma has to be lower than 2. So if gamma is between 1 and 2, then a solution that it is bounded in L infinity this implies that T max is also infinity. This is because we try, if gamma is between 1 and 2, we can achieve the Hadamard growth condition. So we can transform the previous criterion here. If gamma is between 1 and 2, we can transform the previous criterion, but now if T max is finite, then we have that the L infinity norm blows up. This is the key point, having gamma between 1 and 2. But if in the gradient term is not present the gradient of u, then we don't need gamma anymore, so this criterion applies as well. And these are some numerical simulation done by my Spanish colleague, Daniel Acosta-Soba. We took the first problem that we saw, that one was studied by Ishida, Lancaite, and Villaloro in dimension 3, and we try to find a solution that blows up in the equation by putting C equals 0. So we are in the logistic source, there is not the gradient of u. We try to find a solution that blows up, and we did it by following the parameters studied by Michael Winkler. And as we can see in this ball, in the center, we can achieve the blow up. in these conditions here. But now, if we put C not equal to 0, we note that in the interval of gamma, for every small c, arbitrary small, then the maximum of the solution, we can see that starts to going down. So for gamma in our interval and every small c, the solution is bounded. We can note that if gamma is not in our interval of boundedness, then there exists some positive coefficient c for which the solution blows up. So it is very important that gamma is in the right interval. Thank you for your attention.
Thank you very much for this very interesting talk. Are there any questions or comments? If not, we thank again to our speaker, Alessandro. Now let's move to our next speaker, Professor Silvia Frasso from the University of Cagliari, with the title of her talk, Dissipation Induced by the Interplay of Non-Local and Gradient Non-Linearities in Chemotaxis Models. Please welcome.
Good morning, everyone. Thanks, Gamze, for this nice introduction. First of all, I would like to thank the organizers for this invitation and for the opportunity to share my research with you. In this talk, we continue to speak about chemotaxis models. In particular, we will consider chemotaxis model in which the dissipation effect is represented by non-local and gradient nonlinearities. As my colleague Monica Gamze Alessandro said, chemotaxis is the movement of an organism or entity in response to a chemical stimulus. For example, here we have bacteria move towards a sugar crystal, or in this other picture, we have a neutrophil engulf bacteria. Such situations describe, Becker-Siegel models describe such situation and many others, and they study the dynamics of populations as cells, bacteria, or organisms arising in mathematical biology. Such models study the influence of an attractive impact on the motion of the cells toward the chemotactic collapse, which is the mechanism resulting in aggregation processes for the cells, eventually blowing up or exploding at a finite time. The other situation, for example, such model can study the attraction-repulsion impact and the diffusion of the cell and study the competition, the interplay between these situations. In this talk, we consider this type of chemotaxis model. As my colleague said, U represent the density of the cell at the position X and time t. V represent the chemical signal. In the second equation, that can be of elliptic type if tau is equal 0 or parabolic type if tau equal 1, we have that the chemical signal is produced by the cells. And in the first equation, we have that the evolution, the temporal evolution of the motion of the cells is influenced by the presence of the attractive signal V and the presence of logistic source, which is given by this this term, where the factor a u power alpha represent a birth term, and the other two are death term. In the second system, we have the second equation is the same, while in the first one, we have a logistic term of non-local type, plus the presence of the gradient term. In the paper, in collaboration with Rafael Diaz-Fuentes and Giuseppe Villaloro, we studied the impact of non-local and gradient type terms on the dynamics of models A and B by imposing conditions on the parameters involved in some sources to derive the boundedness of solution. Before we state our result, we mention some well-known papers in the literature. Here, in this model, we have a classical Keller-Segal model, as Alessandro said before, where here it appears the presence of logistic term, AU minus BU powers beta. In the paper of Teo and Winkler, they studied the parabolic elliptic model, and they proved the existence of global bounded classical solution if beta is positive and the dimension n is equal 1 or 2, and or in the case b greater than n minus 2 over n times k if the dimension n is greater or equal 3. On the other hand, Winkler proved that if the exponent beta is close to 1, the blow-up phenomena appears. Similar result proved by Lankait and Winkler considers the same situation by studying the fully parabolic models. Here in this model, we have a logistic source plus the gradient term, as Alessandro told in the previous talk. The introduction of the gradient term is a relative novel trend in the literature. Here we mention the paper by Ishida, Lankait, and Villaloro, where they studied this model with a logistic time plus the gradient term. Such result has been extended by Tongxing Li, Daniel Alcosta-Soba, Alessandro Columbo, and Giuseppe Villaloro, where they consider the attraction-repulsion version, proved by that boundedness of classical solution is ensured for beta greater than alpha and if the parameter delta belong to this interval. Now we mentioned some result about model B in the particular case with C equals 0. In the literature, there are some papers, many papers about the parabolic elliptic case, and less paper about the fully parabolic model, to my knowledge. So here we mention the paper about Bian, Chen, and Latos, where they considered the parabolic elliptic version, and they proved the uniform in time boundedness of classical solution if the parameters alpha and beta comply this relation. Such results have been extended to the fully parabolic case by in a paper of Yutaro Chiyo, Gamze Duzgun, myself, and Giuseppe Villaloro. We mention also another result by Tao and Fang, where they consider the same model with tau equals 0 then equal 1. And in particular, they cover another possible range for alpha to guarantee the uniform in time boundedness of classical solution for this problem. Now we focus our attention to our problems, Model A and Model B. We want to show the existence of global bounded classical solutions for this type of models. In the literature, it is well known that these problems, this system, admit local in time and classical solution. So there exists a unique and non-negative classical solution, UV, for some Tmax, which is the maximal existent times to which the previous systems have a solution, such that this time satisfy the dichotomy criterion, or Tmax is equal infinity, or the lim sup as T goes to Tmax, then the L infinity norm of U plus the L infinity norm of V is equal infinity. For model A, there is no necessary to add some other condition. Instead, for problem B, which is the system in which appear the gradient term, it is necessary to control the growth of the gradient term. So we have to require that delta is greater than 2. A fundamental property that we will use in the sequel to obtain our result regard the boundedness of the mass. By integrating the first equation of our problems and exploiting the Holder inequality AOD comparison principle, it is possible to obtain for both problems that the integral of U is bounded. For the first problem, problem A, this bounded is guaranteed by requiring that beta is greater than alpha. For the second problem, it is sufficient that B is greater than 1. Now our aim is to pass to the existence of global solution. We will employ this extensibility criterion. So if U belongs to Lk of omega, for every T belongs to 0 T max, for K greater than 1 sufficiently large, then our solution is global. So T max is equal infinity. Moreover, U and V are uniformly bounded in norm omega times 0 infinity. So there exists a positive constant C, such that the norm in L infinity of U plus the norm in L infinity of V is less or equal than a constant. So our objective now is to prove that the integral of U power case is less or equal than a constant, independent by the time. In order to do this, we define a functional y of t, which is the integral of U power k with k greater than 1, properly large, and we want to construct some differential inequality in order to show that this integral is bounded. We will use two main inequalities. The first one is this inequality, which is a manipulation of the well-known Gagliardo-Niren inequality, and which is called the interpolation inequality. In the paper of Bian and Chen, it is proved in the case of Rn. In our paper, we have extended this proof to a bounded domain omega. The other main tools is the following result, a consequence of maximal Sobolev regularity result, which is proved in a recent paper of Ishida, Lancati, Villaloro, which we use when we study the fully parabolic models. Now we focus our attention on the problem A. By exploiting the previous lemma, we will obtain that the integral of U power k is bounded by requiring that beta is greater than alpha, greater or equal 1, and the parameter delta is greater than this quantity, which depends of the dimension n, and the parameter L, which is the power to the cell density. In the elliptic case, with tau equals 0, we substitute the expression of the Laplacian on V with by exploiting the second equation by its value, so V minus U power L. In the parabolic case, this substitution is no longer possible, so we exploit maximal Sobolev regularity. Once we have in our hands this bounded, we can apply the extensibility criterion in order to show our theorem. By requiring that beta greater than alpha greater than 1 and delta greater than this quantity, problem A admits a unique classical solution, UV, non-negative, global, and uniformly bound in time. Moreover, we have considered the case delta equal this quantity, the limit case. If we take delta exactly equal this quantity, we have to add another condition. So it is necessary required that C is greater than this quantity, which depends on the parameter chi, the constant Cp of the parabolic regularity, and the constant C0, which appears in the interpolation inequality. If we want to insert this result in the existing literature, we can observe that if we take beta equal 2 and alpha equal L equal 1, we obtain the well-known result. In particular, for the elliptic case, we obtain the same condition of Telio-Winkler, beta greater than this quantity, and minus 2 over n times chi. And if we consider the fully parabolic case, tau equal 1, we obtain the result of Zheng, Li, Bao, and Zhu. Of course, if we refrain from considering the deceptive impact from the non-local term, means C equals 0, we obtain that the boundedness of solution is achieved for beta greater than 1 plus L, or also in this case, it is possible to study the limit case by requiring a largeness condition on the parameter B. Now we consider the other problem, the problem in which appear the non-local logistic plus the gradient term. Here we have considered two different situations. First, we neglected the gradient term, so we analyzed the problem with C equals 0. And we obtain that the integral of u power k is bounded by requiring that beta is greater than the maximum from these two quantities. Then we consider the problem with the gradient term, with C greater than 0, and we obtain two different situations. Or beta greater than n times alpha minus 1 over 2, and delta greater than n times 1 plus L over n plus 1. On the other hand, we can take this different range for beta and delta in order to show our statement. Also, as in the previous case, here we again exploit the extensibility criterion in order to show the theorem for the problem B that guarantee the existence of a unique classical solution, non-negative, global, and uniformly bounded in time under this condition on the parameters. Now we can compare our problem with the previous result that we have seen in the literature. In particular, if we neglect the gradient term, so if we consider the case C equals 0, this problem is a generalization of what's studied in the paper of Bianchi and Lattos, in the paper of Ciu, Duzgun, Frasso, and Villaloro, and also in the paper of Lattos, where they consider only the case L equal 1. On the other hand, if we consider the problem with C greater than 0 and L equal 1, it is possible to note that the presence of gradient term improves the range of alpha and beta found in the previous paper of Ciu, Duzgun, Frasso, and Villaloro. We conclude this talk with this final observation. It is possible in some way to choose, to do a better choice between the non-local integral or the gradient term to obtain better dissipation effect, or in the context of this type of system with smoothing logistic source, how the expression provide the dissipation to the dynamics. We consider these two models, model A, this is the model of this talk, and the other model is the problem studied by in the paper of Ishida, Lancait, and Villaloro, where they obtain the boundedness of solution by requiring that beta is greater than alpha, and delta belongs to this interval. On the other hand, for the first paper, where change the gradient with the integral of u power delta, we obtain a better, less sharp interval of delta. We obtain delta greater than n plus 4/2, but in this case, delta is greater than 2. So it seems that the second source has more equilibrium effect than the first. Thanks for your attention.
Thank you very much, Silvia, for this excellent presentation and the results. Are there any questions or comments? If not, just a curiosity. Have you ever considered the non-linear case for the term of diffusion term?
Yes, in the paper with Rafael Diaz-Fuentes and Giuseppe Villaloro, we also studied the case with nonlinear diffusion, nonlinear sensitivity, and we obtained some condition about boundlessness of solution, which involves more parameters, so the conditions are more rich.
Perfect, thank you. Thank you again to our speaker. Now our last speaker for today, for this session, is Professor Giuseppe Villaloro from the University of Cagliari. And the title of his talk is Exploring the Dynamics of Keller-Segel Models with Positive Total Flux.
Thank you, Gamze, for your introduction. And of course, thank you to everybody to attend this talk. Also, thank you to the audio and video technician who is working hard for us. And yes, let's say that several things have already been explored by our previous speakers, so I will skip different slides. In any case, I just want to mention that the main idea of this work is essentially to change the boundary condition of our Keller-Segel model. So far, the boundary condition for all the Keller-Segel models that we have observed were concentrated, let's say, given by the fact that the boundary condition have some Neumann boundary condition, homogeneous Neumann boundary condition. On the contrary, here, we want to observe what happens when we change this boundary condition. And this is essentially our main idea. Of course, Robin boundary conditions are very famous in literature, but so far, at least to our knowledge, were not used in Keller-Segel model. So we want to compare the known result for homogeneous Neumann boundary condition and check what happens when these homogeneous Neumann boundary conditions are substituted by Robin boundary condition. I believe that what chemotaxis is very clear at this stage, because we have talked about the movement of cells inside a domain, and we can observe that when the concentration of the initial mass is very high, or the attractive chemical is high, there is a blow-up. So the model stops, and there is a accumulation of cells inside the domain. The model, as we have seen, okay, so I can, let's say, be rather fast in this part, is composed by these two equations. So the first equation for U, and the second equation for V. And essentially, when chi is very large, we may have blow-up, conversely not. We want to observe that in one dimension, there is no possibility that blow-up occurs. So in one dimension, the solution is always bounded. Conversely, in two or higher dimension, we can have blow-up. Please, I insist that we are in the situation where Neumann boundary condition, which essentially means, so with Neumann boundary condition, we have this by integrating the first equation, exactly by integrating the first equation, we have that the integral of U, the integral of U is bounded. So this is a function of t, and this quantity is always bounded. This is strictly connected with Neumann boundary condition. And of course, having this information is crucial. Without this information, we cannot carry out any kind of analysis. So if this one is not bounded, our model is useless, totally useless. And I insist, this property is totally connected to the Neumann boundary condition. Okay, so here just some numerical simulation in 1D. We have observed that any solution is bounded. Yes, here there is some simulation in a square where we can observe that conversely, if the initial distribution is high, we may have blow up. In this case, we have blow up in the center of the square. In 2 dimensions, we can have the blow up situation. Okay. We have some problem, I don't know. Non so come si voglia. Okay, so we have talked about the crucial property. It has the conservation of the mass that it derives actually by integrating this equation, and I insist by using this Neumann boundary condition. So we have that the mass is bounded, here in this case, and we may develop further analysis in order to show whether all the norms are bounded or only the L1 norm is bounded. Okay, here there are many variants of the Keller-Siegel model. So just I give you some hints about the variants of the Keller-Siegel model. And I want to underline that even though we can change the boundary condition for V, just for V, in all the cases, this is the Dirichlet boundary condition, Robin boundary condition, but the common denominator of this model is that the total flux is 0. So once more, if you have that the total flux is 0, when you integrate, the boundary part deletes, and you follow having boundaries of the mass. So let's say that the L1 boundaries of the mass is always preserved. So the total flux is always 0. Okay. We want also to mention this other result, just because we will check later, let's say, its interplay with our main problem. So when we consider the classical Keller-Siegel system with some logistic, this logistic here, we may have that blow up may occur if C equals 0. So as Alessandro told, we are dealing with a logistic term including growth, natural death, and accidental death. And the question is, what happens if C is equal to 0? So if there is no accidental death, and K is small enough. So we may have blow up for C equals 0, okay? We may have blow up for C equals 0 and for value of K small enough. Conversely, as Alessandro told, when we consider C, we may prevent blow up whenever gamma is large enough. So we may have blow up without C, but including C, we may prevent this kind of blow up. Okay, this is the paper that also Johannes mentioned. Alessandro mentioned. Okay, now let's skip to our main idea. So our main idea is considering positive flux. Positive flux means that we consider Robin boundary condition for V, this boundary condition for V, and another boundary condition for U. And I want to underline that for this value of H and alpha, both U and V are leaving the domain. So separately, both U and V are leaving the domain. Conversely, the total flux, which is this expression here, is positive. The total flux is positive. if we compute this sum, this addition, we have that the total flux is positive. So it means that when we integrate the equation for U, we will have a boundary term coming from the total flux. Essentially, we have the equation here, the boundary condition, and when we integrate the equation, converse it to the previous case, now alpha is not 0, so we have that the mass is increasing. We have that, we don't have this situation, but we have that the derivative with respect to the time of the integral of U is greater than 0. So it means that the mass is increasing, it's not bounded. So we do not have this situation. So without this situation, without this information, we are not able to control anything. So we need some artificial, let's say, but also natural source which prevent this uncontrolled increasing of the mass. So this can be the behavior of the mass. So the mass may increase and remain bounded. Conversely, the mass may blows up at finite time, and if the mass blows up at finite time, there is no way to continue the study because also the L infinity norm blows up at finite time. Or conversely, we may have some blow up of the mass in infinite time. In any case, I insist, we want to have some property of the solution, and the most easy property is the boundedness of the mass. Okay, so here we have just some numerical simulation in order to show what happened in a circle in which we have posed this Neumann boundary condition. We can see that at the boundary, the cells increases. So this is the evolution of U. This is the initial distribution, and one is the final distribution. And this is the numerical simulation, the video, say. So we can see that with time increasing on the boundary, the cells increase as well. I have to wait just a second. Okay. So how to control the mass when we have the total flux, the positive flux, sorry. So we just recall this behavior of the mass in time, and we are able to invoke the trace embeddings. So in general, we have that kind of information when we use trace embedding. So we are able to control an integral on the boundary by means of two integrals on the entire domain. So let's say that with this kind of general trace embedding, we can control the integral on the boundary by means of the integral on the entire domains. So essentially, we want to control that integral over there, which is on the boundary. And by means of Young's inequality and trace embedding, we can say that by controlling that integral on the boundary with the trace embedding, we have that now the evolution of the mass is controlled by this term. Please note that there is no boundary integral on the boundary now. So the idea, of course, is that by manipulating the second equation for V, we have this expression for the evolution of the mass. So it is clear that we need, in order to control the mass, to insert in the first equation some very strong logistic in order to balance exactly this part here. So we need, in order to control this part here, we need to add a strong logistic which can absorb that part. And this is the reason why we need to use this classical logistic which takes into account the growth, natural growth, sorry, the growth, yes, then the natural death and the accidental death. So by means of this term here, by inserting this term here, we can control these two integrals. So essentially, we have dealt with this problem, which again is a parabolic, elliptic, or fully parabolic problem with positive total flux. And the idea is that we need a strong B and a positive C. So a large B, B is the coefficient in front of the natural depth, and a positive C, of course, which depend on the parameter of the problem, in order to have boundedness of the mass. So I want just to underline that the message, according to me, is this one. If we have positive total flux, apparently, in order to have boundedness, some strong logistic is required. And with strong, I mean a logistic with both accidental death, with both natural death and accidental death. And I want to underline that it is the presence of the gradient U squared there is not just connected to the trace embedding. In fact, this paper is a paper by myself, Sita Frasu, Yuya Tanaka, and Kadisha Bagai. Kadisha Bagai is a very clever woman. Silvia also is. Yuya also is. I'm not clever, but Kadisha could avoid to use trace embedding, so she did not use trace embedding in order to have boundedness of the mass. Despite that, she also had to make use of the gradient of U square. So the gradient of U square there is not just connected to the usage of trace embedding, but even though you use a very clever way proposed by Kadisha, she needed the presence of that gradient nonlinearity in order to control the mass. So I believe that in both cases, when positive flux is considered, you always need not only the gradient, the presence of the gradient, but the square. You need U square and gradient of U square. With lower power, I guess that it is not possible. So I believe that, yes. And thank you for your kind attention.
Thank you very much for this very nice talk, Giuseppe. Are there any questions or comments? Please.
Very, very interesting talk. And my question is for the parameters B and C. So it is, when you say C positive and stronger B,
yes,
you mean that the presence of the gradient term in the logistic is just to apply, just to bound the mass, and the work is done only by the B?
Yes, essentially, you can have in general boundedness of the mass, but some unboundedness for some LP norm. Okay. For instance, you know that in 2 dimensions, for the classical Euler-Siegel model, in 2 dimensions, the mass is bounded, but if the integral with U0 times chi is large, you have blow up. So just the boundedness of the mass is not enough in order to have uniformly bounded. Conversely, in this case, with the boundedness of the mass, the rest is free. So yes, just having the boundedness of the mass. In fact, the condition that you have seen is just to have the boundedness of the mass. The rest is automatic.
The condition on B also?
Yes, the condition on B is just to have the boundedness of the mass.
Okay, I understand.
But take care that U square is very high. The 2 in the U and the square in the U and the square in the gradient are very high. But this, according to me, is extremely connected to the flux, which I recall you, which is UV, the flux. It's proportional to UV. So the total flux. And if you note, UV is linear times linear is square. Let's say it's like, let's say, K square. And this square here is exactly the one that you need in the U and in the gradient of U. In fact, there is another paper by another guy who he studied some flux. It is very important, flux positive, which behave like U to the power P. Okay, sorry, absolute value, U to the power P. Okay, with P between 1 and 2, which I want to underline that this value, this power here is less than 2. This guy obtained boundedness without the gradient term. Without the gradient term. But this P is smaller than 2. I don't know if I explained.
Yes. Thank you very much.
You're welcome.
Any other? Please.
In the case of positive flux, so it's not necessary to have the gradient term in the source to have the global existence or boundedness.
In this case here?
Also, only in this case?
In our case, we need the gradient term. But
for the global existence.
For the global existence, yes. But please take care that is quadratic. This growth is quadratic. U times V, you can interpret like U to the power 2. Conversely, the other guy with a sub-quadratic power obtained the boundedness without the gradient term.
Without. And about the blow-up, in the case of flux, positive flux, and without the gradient term, for instance, are there some results,
no.
also numerical?
So, to my knowledge, there is no result, because the only information that you have is that with positive flux, the only information that you have is that
with the Robin boundary condition. No?
Yes, but the only thing that you know is that, or at least that I'm able to observe, is this, that the mass increases. But this is not sufficient to say that there is blow up, because an increasing function can also be bounded.
Yes, but the source term is of logistic type.
No, without any source.
Without source.
Without source. So we need to add a source, because in order to be sure that...
For the boundaries.
Yes, for the boundaries. Because unfortunately, we do not have, we have something like this, integral on the boundary UV, and we are not able to go in this direction with this sign. By using trace embedding or the Kadisha method, we are just able to continue in this sense. And so we need to put some strong logistic in order to control the mass.
Okay, thank you.
You're welcome.
I think it's okay. If there is no further question, we can conclude our session. Let's thank again all speakers, participants, my colleagues, organizers, all technical support. So thank you. Thank you again, and enjoy the rest of the conference.